Thank you and hello everyone. Thanks for joining this session. I feel actually a bit bad because the previous one was just cut before the conclusion, which is usually the most important part for me. Anyways, I hope we can interact with the speaker after the two sessions, the two presentations. As you can see, there's a bunch of folks in this research. And I would say that Victor and I are both honored to represent all of them. It's been a very interactive project with many people, many researchers. You can notice Eric from AD-Link, which is best known as the lead developer of Cyclone DDS, which has been our expert on DDS in this journey. And then we have several researchers from TX1 Networks, which is a Tremicro plus Moxa joint venture specialized in OT security. So I would like to thank also Talun, Chizuru, Patrick, and Mars from TX1. Our goals in this project is to take a deep look at the standard of DDS, and you might already anticipate why it is interesting for our community and your community. Because the idea is that we wanted to find security issues in a proactive way. Because in this community and in these applications, you can simply not afford eliminating bugs when they are already in production. So what we want to do is to try to anticipate as much as possible the finding of bugs. And overall, what we want to do is to raise awareness, and that's why we are here in this forum. We are trying to address both the security community, because almost none of them, when I presented this work at a security conference, were aware of DDS. They were actually a bit shocked to learn how much DDS is used in everyday systems. And finally, we would like to suggest some mitigations to address not just our issues, but to address what we think is something a bit deeper. Okay, so since we are going to talk about DDS, I thought I could spend just one short slide on it. You might have heard of it, of course. You might be using it, but maybe you don't know the deep details. It's a middleware protocol. So it's used to create communication layer between whatever you want in a peer-to-peer fashion. So you can have sensors, actuator, control applications all talking together in a system, and you want them to communicate in a very efficient way. It has the notion of typed data. So what you can see here is an example of a very simple type. It's a hello world type only having two fields. You specify types like you do in C or protobuf, if you're familiar with protobuf, and then the library takes care of everything. What you do is, as a programmer, you just write code, and everything else is taken care by the library, by the DDS library, which includes serializing, deserializing, participant discovery, and so on. And plus there are other nice things on top, such as QoS and also security extensions. And I guess that the main reason why we wanted to be here is that DDS is the default middleware of ROS2. So what before was TCP ROS, if I remember correctly the acronym, now is becoming DDS. So unless the user wants to change that part of ROS because maybe they need some custom deployments, every ROS2 installation is going to have DDS in its heart. And so all of the findings that apply to DDS, of course, also apply to any ROS2 installation. I was talking yesterday about finding estimates of how many ROS2 systems are around. Of course, it's a very difficult question, but can we make an educated guess? So it seems that 60 to 70%, I don't know if it's accurate, but please ping me or write in the chat, 70% of the robots use some sort of ROS, right? And looking at the metrics that I found on the ROS2, on the ROS website, in 2019, ROS2 adoption was like 5%, below 5%, and now we are above 55%. So if we make an educated guess, we can say probably 20% of the robots are based on ROS2. If you have other numbers, please, I will be very interested in knowing them. Good. This is the title of what you see in the title is also the title of a presentation that we gave at Black Hat Europe, which is a security-only conference. Now you notice that I didn't say DDS is critical, don't use it. I said DDS is critical, let's use it securely, right? There's no such thing like a protocol is secure or a protocol is insecure. Simply, security doesn't mean having encryption, having authentication, having the reassuring lock in your browser, and so on. Security is much more than that. So first of all, you need to have a culture. You need to embrace the fact that software can have and will always have vulnerabilities. Once you are aware of that, you can start bringing in your organization the skills or the people who are needed to build a process to ensure that there is a process thinking about security and taking care of security. There's no way to ensure that the software is going to be secure. At the end of the day, you're going to receive some notifications like this one. I'm not going into the details of these, but this is just an example of what security researchers do. They do find vulnerabilities and they report them. And at the end of the day, they get assigned a unique number called CVE. And as a developer, as a DDS developer, as a ROS developer, anyhow, you're going to receive a report that say, hey, that researcher has found that vulnerability, what you're going to do. That's why you need to have a process, right? You need to be able to understand, you need to be able to assign it to the right developers and so on. You have to have a bit of those skills also as part of the developer skills. By the way, the table is much longer than that. So I think it's better that I think that instead of looking at this table, you like this one better, because I think it's important to put things in perspective here. When you have a final system, you're not going just to have a custom software. You have to understand the chain of software that is part of that. So what we are interested as researchers in this space is looking at the standards, because, well, when you have a vulnerability in a standard, that's going to impact all the way until the production for many years, because it takes years to fix an issue in a standard. We're also interested in looking at the distributions, and that's what we did for the past 6 to 8 months. Because if there is a bug in a distribution, then if that distribution is built into some products, then you have to also take care of going back and fixing not just the implementation here, as well as the system here. What is concerning for most of the ROS2 folks here is that, as I said at the beginning, whenever you have whenever you have ROS2, you have DDS. And so make sure that you are aware of that part, because the attackers are really aware of this. So what's interesting for an attacker from this point of view are 3 important points. First point being supply chain compromise, which means that they are interested in targeting the developers in order to infect a project file. This has been happening for a few years. Increasingly, they are interested in exploiting network reachable bugs and so on. And they are least interested in exploiting physical access bugs, but of course those can happen. And of course, if there is a design bug, they are very interested in that, because they know that they can be sure that that bug is going to be there for a long time. So with that, I would like to give the hand to Victor, who is going to tell us how we found some of the bugs that we found. So I think that you have to take control, Victor.
Trying it.
You have control now. Perfect.
Let's see if it works. I think it does. Okay, so thank you, Fede, for a fantastic introduction. Hi, everyone. So actually, it's pretty fun how Federico and I encountered together on this piece of research. For those of you that attended last year's ROS Industrial Conference in Europe, You may remember that I presented a bit of work related to essentially security research on ROS1 systems and how I created a dissector using SCAPI of TCP ROS and UDP ROS. Now, after that, and as promised last year, I started porting that work into DDS, into RTPS, and that's the point where Fede and I encountered. We both were doing something similar, pretty much the same, implementing the same thing. So we said, well, why don't we just partner up and push this together, right? And that's one of the beginnings on how this started working. And that's what we are presenting in a way today. And that's the first slide I somehow would like to introduce to you. This is the result of, again, a cooperation between not just Fede and I, but many others. We open sourced, and right now, as of yesterday, I think it's been merged upstream within the SCAPI GitHub repository, an RTPS layer for SCAPI. For those of you that are not familiar with SCAPI, SCAPI is a Python-based interactive packet manipulation program and library that enables users to send, to sniff, to dissect, and forge network packages. In this case, it does so for RTPS, which, as you may know, it's the underlying wire level protocol that DDS uses. We extended these SCAPI capabilities to RTPS layer, contributed, and now it's possible for you to craft packages that actually can interoperate directly with ROS2 nodes, with DDS endpoints, and related. You can see in the screen right here, actually the simplest package you can craft, and that is somehow scripted with Python code, and you can see the relationship between essentially what you write and how it gets represented. Here is a more complex one, a more fun one. In this case, we're constructing with the RTPS dissector and package crafter a package that's targeted to exploit a flaw in OpenDDS, one of the DDS implementations we explored. And it particularly leads to ROS2 nodes crashing and execute arbitrary code due to DDS not handling properly the length of the PID built-in endpoint QoS, which you may see in the slides. That's a parameter within the RTPS's data submessage, particularly. This flaw, as well as many others, were found in a combination of using static analysis and dynamic analysis. So let's take a step further and dive deep into actually what approach we followed and what we could present today to somehow raise the awareness of security within the community. So the average attacker would typically follow these three phases, which we will explore now between both Fed and I. The first thing he or she will do will be essentially trying to identify your robot. And this is commonly known as reconnaissance, which groups together both footprinting and fingerprinting. I will leave the details aside and just focus on essentially general reconnaissance. And again, that's targeted to find your robot, either in the widespread internet, and maybe in the future we will share some data about that, or specifically within a subnetwork as the one you may have in your industrial workspaces or in your homes. That's the first step. The second one essentially is once found the robot, we can start triggering certain flaws we may have identified in the corresponding communication middleware implementations, DDS in this case, and we'll see how we will present how we can mess up actually with ROS2 traffic remotely, and how this can lead to essentially real-time indeterminism in overall real-time, compromising real-time in a way. Third step we will present, which is also somehow related on how average attackers do behave, is once you've somehow identified and realized that you can compromise the system, how you can pivot across subsystems within the robot and essentially lead to crashing particular ROS2 nodes, or even just craft packages that particularly take control of individual nodes to modify its behavior. In this case, we will just show a simple POC that crashes a particular node and leads to an actual very silly crash. You will see it later. But this is the average flow that we believe will bring value and awareness. So in here, and it does appear that the GIF is not playing, right? No, it's not.
No, it's not.
So unfortunately, due to technical issues, we cannot see the actual GIF, but I can at least try to describe it. So the actual recording was showing how essentially we craft in here a simple package That's particularly targeting the reconnaissance of the one of the DDS implementations, particularly Cyclone DDS. And we show how by launching this package out there, we can actually get back responses from any ROS2 node that's using this DDS implementation, again, Cyclone DDS. We also demonstrate as part of this recording how if we switch from Cyclone DDS to, for example, Fast DDS or any other, we actually encounter how they don't always respond in the same manner. You've reshared the screen, right, Fede?
Yes, here you should see the GIF that Victor is talking about.
Thank you, Fede. So, so yeah, essentially, as I was saying, if we switch to a different DDS implementation, we'll see how the responses are different, which essentially shows funny behavior of how DDS implementers, DDS vendors take liberty on implementing how discovery works. This difficults a bit our work from a research perspective, but it is fully feasible. Actually, we by modifying the package we craft slightly, we're able also to identify fast DDS-based ROS2 nodes in the network. And by no means we want to claim that, of course, Cyclone DDS is less security aware than fast DDS. Actually, the other way around. We found many flaws in fast DDS, which were very low-hanging fruit, which we did not in other DDS implementations. So nevertheless, a reconnaissance as of today with DDS systems and by default thereby with ROS2 nodes is pretty much a given. And as of today, there's no actual mitigation for doing reconnaissance as per the ONG specifications. So we can literally discover these nodes either, again, directly in our networks or out there in the internet, and we will share some data about that in the future. I'm gonna ask for the control again, Fede, in case I can.
Yes, the next one, yes, okay. Let me share again the slides.
Yeah. Oh my.
Yeah, it's coming up. And okay, take control.
Control again. There we go, I think.
Yes.
Awesome. So I think at this point, I'm passing it up to Fede to continue on this attacker's path, and he'll tell you more about how we can actually mess up with ROS2 traffic.
Thank you. Right, so I guess that I will simply go back to simple sharing because we're sharing videos, and so it makes more sense to. Okay, so here is a simple demonstration of how discovery is supposed to work. So the speed sensor sends data over the network to a broadcast domain, and this could be in a car or airport or any other scenarios. And usually the participants answer back in in a few milliseconds, right? What we found out is that we can craft packets in a way that the victims will be, another victim will be flooded by network traffic by exploiting the fact that if the discovery doesn't receive an acknowledgement, what happens is that it's built in the specs that the initiator will have to keep sending packets. And that's exactly what we are leveraging in order to discovery DDS nodes up in the open internet. We are currently scanning. But the downside of this is that this can be abused also for amplification, which means that, let me go back quickly, which means that if you look up the traffic, how it looks from Wireshark, you will see that if you spoof a packet coming from obviously a non-existing participant, this is the IP address of the Google DNS, which is not exposing any DDS node, you will see that the participant in the network is trying to actively discover whether there is really a DDS node on the other side. And it will keep going on like that forever. For example, I've been running an internet scanner for a couple of days, and there are some hosts which I contacted using the probes, and they keep sending me traffic. They never stopped sending me traffic for 2 days with no signs of stopping, because I'm not answering back to them as a participant, right? So this is an actual problem that is actually, we found it by mistake because we were playing around with some some of the key fields in a packet, and we discovered that by changing the locator field, which is the IP address of the nodes that you want to discover, this behavior gets triggered. But once we went back, we discovered that the issue was actually in the specifications, because the specifications do not allow the implementation of some things like whitelisting or things like that, because it has to be like this. I mean, this is how discovery works. And it also works if DDS security is enabled, because of course discovery must be able to occur even if there is DDS security enabled. And there are, of course, issues open at the OMG issue tracker to take care of this. Now, I would like to give it back to Victor, but if there is another GIF, an animated GIF, I better keep the control of the screen, Victor. Yeah. What do you think?
Let's stick with that, and I'll just ask for its night.
Yes.
Thank you, Fede. So, so anyhow, Fede showed fantastically fine how we did find that flaw which allows for reflection attacks, and that can be triggered, by the way, with multiple essentially intentions, meaning that this reflection behavior we observed can be actually performed and reflect traffic to one or multiple targets, meaning that eventually you do overload the traffic on that particular endpoint, compromising again real-time interaction with other network endpoints or other ROS2 nodes in the network. So at that point, we thought we should show how we could trigger this with a real robot. And what you're seeing right here is actually a security flaw that affects solely RTI Connext DDS. RTI Connext DDS is a proprietary closed source DDS implementation. And the flaw we found itself is a segmentation fault caused by a malformed RTPS package, which can be triggered remotely over the network. This is a different security flaw. In a nutshell, the Connext, the DDS implementation serializer in RTI's implementation throws an error while digesting this package. And this leads to the corresponding ROS2 node to exit immediately, causing, of course, denial of service, but in addition, due to how essentially the computational graphs get composed. Depending on the node's actual computations, it may lead to safety issues due to the fact that the communication is interrupted immediately and no further essentially interactions with the corresponding topics happens. This flow, by the way, also affects both publishers and subscribers, and an attacker could selectively crash specific nodes, which may compromise the robot computational graph by achieving beyond DOS, beyond denial of service, malicious objectives. The clip itself, which is reproducing over and over, is showing how the flaw is exploited in a simulated Turtlebot 3 robot, which we used in past seminars for security in the ROS world. Now note how the teleoperation node is first launched and stopped, demonstrating how the corresponding topic's velocity values are set to 0 after the node finishes and it gets stopped in a normal manner. This avoids the robot to move in an undesired manner. If instead we stop the actual node by crashing it, exploiting this flaw, this vulnerability, we can observe how the last velocities are kept infinitely, leading the robot to crash against the wall. The interest of this flaw is that it somehow or somewhat shows how easy it is to compromise a computational graph built with the best in the world DDS solution. And these are not our words. Of course, this is what RTI is claiming. And thank you, Fede. And that's a screenshot just taken from RTI's site. And we just found interesting how it does not just seem that open source with commercially friendly licenses are indeed vulnerable. As Fede was pointing out, security is an end-to-end effort, not a product, but a process. You need to over and over assess. And it's interesting how, again, this security by obscurity sometimes concept we tend to accept is proved wrong by our research. It's essentially showing how even those ones that claim to be performing best actually do get compromised equally fine. Now, this video you're seeing over here is actually something I cooked in my home, and I'm using over there, as you can probably see, my diaper tester. And again, apologies for the home video, but that's what we have right now. So the Turtlebot was commanded to stop just in front of the robots with the corresponding teleop node. But what happens is that an attacker is triggering the crash just exactly before the actual stop command is sent. And of course, the velocity is kept. This is essentially demonstrating the same exact flow that the previous GIF was showing, only with a real robot and only with a ROS2 real computational graph on an actual physical system. Next slide, please. So with all of this, we hope that by now you do have an understanding of the actual current security situation within ROS2, which does not necessarily just affect the ROS2 core layers, including RCL, RNW, and related, the adapters as well, but also the under layers, also the communication middleware in this case, and how by exploiting the communication middleware, we can compromise a full ROS2 system. Now, we do have future work planned, and particularly on these 5 directions. The first one is we plan to continue researching DDS, and likely will target in the near future secure DDS, essentially plugins and specification. Early results show that and hint that similarly security might be overly advertised at this point for the security in DDS, since various issues are to be addressed, and also many of the flaws we presented today do affect directly even those implementations with the DDS security plugins enabled. The second bit is that we plan to improve the OMG standard. This is our intention. Of course, this requires OMG to also will to cooperate with us. We have requested repeatedly meetings with the right stakeholders. We are still waiting, but thankfully we have Eric within our team, which is very influential in those, I would say, areas. And we're navigating towards essentially reaching convergence there, and maybe applying some suggestions that would overall shape up the OMG standards to a better security-aware attitude. The third one is that we do plan to maintain the RTPS dissector that has been just merged into SCAPI. And of course, since we will explore the security plugins, we may contribute back as well these extensions to actually also test the security plugins within RTPS and DDS overall. We also are in the process of actually contributing back, not just for ROS2, but a ROS1, TCP ROS particularly dissector. And there's already a pull request. If you're interested, you can reach out to me, and I will point out to you to the right place. This dissector can similarly be used to challenge ROS1-based communications. And last but not least, there are more talks coming up. This is actually the second public appearance we make with this work. The previous one was at Black Hat, which is to many one of the most well-known and famous security conferences. We will also be in a few more security conferences, and we will also be presenting this in the ROS2 security working group. So again, trying to raise the awareness. Maybe the last slide. Key takeaways, and in a way, a few messages on how to improve ROS2 security. It's been widely mentioned, security, throughout this sessions so far, which makes us very happy. Just 3 tips from our side. First, maintain a security first attitude by following a DevSecOps approach. If you don't know what this is, or you would like to learn more, there's prior public research we published, which you can refer to. Second, please periodically perform security assessments. Either you yourselves by, as Fede said, hiring the right personnel, or partner with researchers that do so for you. Third and last, but not least certainly, is please do participate in the ROS2 security working group. There's very little activity in the security working group. We're trying to revamp this. We're hoping that disclosures like this, which have been responsive at every single point in time, aim to raise the awareness and to get more people interested in security. And as pointed out in the slide, please do consider the fact that to make ROS2 secure, real secure, we need to have an end-to-end approach, and for that, the whole stack in robotics needs to be assessed. And with this, I would like to thank you for your time, for your interest, and we're more than happy to take any questions.